You able to hear and see my slides?
Yes to both.
Okay, perfect. Let me know when I can start.
Great. So our final talk of the session is from Niharika or Ari Sravan from Caltech. Over to you.
Hi, so I'm gonna start my timer right here. Hi, so yes, my name is Niharika. I'm a postdoc at Caltech. And this is a talk that's going to be largely based on a paper that is on the archive right now. I'm going to talk a little bit more in detail about that paper, but I think the motivations sort of borrow a lot from stuff that have been discussed in this conference so far. So to start off with, I think it would be nice to set the stage for where we find ourselves. So there is a situation right now that the data that we are getting from surveys is largely determined by their own schedule. And for many science cases, especially if you think about Rubin, the cadence is not going to be sufficient for science inference. At the same time, we will be limited by follow-up resources that are going to be expensive. And these can be of a variety of types, right? So you can have resources that you might have in the UV or the infrared, perhaps they're in the space. Maybe you want to collect some spectra. So with this deluge of data that we are going to we have to make very smart decisions about how we are going to be able to allocate resources such that we are getting the most out of the investment that we are putting in. The challenge obviously is that these decisions need to be made often with incomplete information, which means that for transients like the ones I'm usually interested in, you probably don't see most of what the transient is doing. And you probably need to make these decisions quite early in the evolution. You also need to be able to be adaptive, which means that once you make a decision and you acquire data, you need to be adaptive and you need to do this fast and you need to do it at scale, which means you will be you'll have a huge amount of deluge to deal with. So there is a need in the field right now to be able to have systems that can organize such follow-up. And in our 2020 paper, we denoted this as oracles. Dan has spoken to you yesterday, and he's given a talk on refit, which is the first manifestation of such an oracle. So I would refer to you to his talk for details on how this is looking like in practice. My work has been really about the theoretical implementation of how this might look like. So I really want to make sure that the mathematical side is a little well-founded at this point. So number one, let me just state the problem up front. What is the problem that we have? We have the problem of that we have a given set of actions we can choose from. So if you imagine this light curve that's occurring, you may want to fill it with data in the photometry that you see. You may want to fill it otherwise. You will often be subject to some budget constraints, which means you can't follow up literally everything that you're considering. So you have to make these decisions smartly. And you want to do that such that after the episode is over, not while you're collecting the data, but in hindsight, when you're done, that you have maximized your objective. The caveats when you consider a problem like this is that the only your current actions, things that you are considering right now, will reveal outcomes. So if you think about a deck of cards that are being unfolded as a function of time, if you take a bunch of decisions, only the decisions that you take at this current moment will be revealed to you. So you can only turn the cards over right now, but you have to consider anything else that you have to do in the future. So there is this probabilistic trade-off, explore-exploit trade-off that you have to keep in mind. Another thing, because this is a sequential decision-making problem, you cannot undo, which means that if you've revealed a given card, you spent your credits over there and that's it, you're done with, you have to move on. And at the same time, if you have made an investment and you get some data, you need to be able to adapt to the information that you just received. So let me just put forward a really cartoonish picture of how this would be implemented. And bear in mind, this is extremely simplified. And of course, it's significantly more complicated than what I'm showing here, but this is just for illustration. So imagine you're in a situation where you're seeing a transient that is just happening and you see just a bunch of data points taking place. And you find yourself at a current moment in time, which here is this red arrow here. At this moment, the first thing you want to do is to define your action space, which means mathematically, what exactly are the set of actions you can potentially take for this event? And again, this is a simplified setting where you're looking at that one event. We don't have multiple events we're considering. But for this event, say for example, your action space is that you can take data in green, you can take data in red, you can take data in green and red, or you could do nothing. So this is the most simplified setting you have. And in this case, you're only considering actions today. However, of course, in the most generalized setting, you probably are considering continuous actions, and you may have to consider costs and budgets, and in many cases, variable costs, depending on how expensive it is to collect the data that you're interested in. So once you have done this assessment, step 2, you need to be able to estimate what you might get if you took actions mapped to the action space. So for every data point that you could collect, say, for example, here I'm interested in seeing whether I want to get data in red, you want to be able to estimate what the utility might be for getting that data. And this could be, for example, done using some forecasting, probabilistic forecasting that you can estimate to see how well you're doing with your objective. So this portion where essentially you estimate what the outcome states are, you then take it around and you say, okay, so I take this action, here is the outcome state that I get. How useful is it for my particular outcome or my particular science? So say, for example, you're interested in classification, you can answer questions like, okay, how much is my classification accuracy or your F1 score or whatever metric you may be interested in improving if I were to constrain that space much better? This is basically the part where the science portion comes in. So say, for example, we're interested in doing inferencing for the physics. This is where we may be targeting we may be targeting parameters for a physical model, the kind of which I think I'll go into a little more detail later. That would be a place where that would come in. And you could also use this for model discrimination. You could use this for hypothesis testing. I mean, essentially, this is basically your notion of what you want that should go in the model. So at the next time step, once you've made the decision, once you've made the determination as to how your actions map to various notions of utility, how useful they are, you basically pick the one that gives you the maximum expected utility. You take that action. So in this case, for example, you determine that getting data in red was the best for your setting. You collect that data, and in the next round, you do the same thing. Basically, you repeat. So you right now in the next time step, and you right now have to make the same determination all over again. Now, like I mentioned, this is extremely simplified, of course, because you're being extremely myopic. You aren't taking into account future actions that you may or may not take in the future. And the goal is eventually to take an optimal series of decisions that all relate to one another. But the hope is to show you at this point, like how the steps kind of work through. Essentially, in the recent paper that we put out, we actually tried to solve this problem in a first order setting by looking at type 1a supernovae. And type 1a supernovae is loved and beloved by a lot of people because they're very important for cosmology, for getting the Hubble constant, for constraining the dark energy equation of state. And in addition, because they're such useful standard candles, you can use them to get an estimate of the local anisotropy by getting an estimate of things like growth rate and velocity flows. So before we move further, I want to make sure that we're all on the same page about how to do cosmology. And this is just to make sure we understand what the algorithm will be doing when we get to that stage. So essentially, here's what happens. You have a bunch of light curves that you collect for a whole host of type 1a supernovae. And for each light curve, so for example, here is one light curve that I'm showing, you will fit it to some models that would be that can map to a standardizable setting. So here so for example, Sol2 is a very standard model. It consists of 4 parameters. So X0, X1, C, and Z are 4 fitting parameters. And what you will do is you will fit every single light curve with these models, and you try to get the constraints for these fit parameters. Now, for the entire set, once you go ahead, you fit your for your entire type 1a supernova sample, once you fit it, you will be able to take these parameters and you can constrain your cosmology, which is a function of these parameters for the whole sample. And the point is that if you were to minimize the uncertainty on the light curve fit parameters for for the entire set, or maybe even one, you will in turn minimize uncertainty on the cosmology because it propagates that way. So if you could have a design where you were making decisions to be able to minimize the uncertainty on a standardizing model, you will do well for your cosmology. And so this is the example that we took as to what we would use for our objective. So let me just give you the problem statement. The problem statement was that we would like to add photometry to branch normal supernova 1A light curves. So these are the ones that will be useful for cosmology that were derived. So this was done in the past, but we pretend like, we were real time. So these light curves were taken from ZTF1 public survey in GNR. And we tried adding data in GRNI to minimize the total uncertainty, net uncertainty. So basically you just like take the A optimalities, just take the diagonal of the covariance matrix, and you try to minimize the uncertainty on that. And the reason we looked at I-band is because we know from related work that the radar filters are very important for precisely estimating H0. It's also useful for looking at explosion mechanisms. But then again, sort of looking at future surveys that are in space, and we want to be able to use some of these resources much better. I'm thinking of JWST, I'm thinking of Roman. You want to be able to collect data in UV or IR. So it's useful to sort of look at a time series and not just augment the time series in itself, but you sort of look at it in a parallel domain as well. So the way we solved it, and this is I promise, the most technical slide. So we basically treat the problem as a non-stationary Markov decision process with a finite horizon. So we took 60-day episodes and we defined our state space, as I was mentioning earlier. So you need to go through these steps. So basically we defined our state space as whatever you observe, any data that you might see from the survey. So we did 10 Monte Carlo simulations of what the survey could do. And this was just a number that we were playing with. And we would allocate remaining budget randomly. And essentially this was approximating. So we're not doing optimal series of actions. We're taking myopic actions, but we're also taking average actions. So this is not the most optimal algorithm, but it is still better than doing everything randomly. And we show that because we do compare and we do better than just doing random. We consider the action space, which corresponds to all sorts of combinations that we would see in GRNI. We consider a deterministic reward model. As I mentioned, we wanted to target cosmology, so we were looking at A optimality. In this case, we used solved 2 parameters and photometric redshift, because I think in practice, you would not know for the supernova what, you're not guaranteed to know what the spectroscopic redshift might be, so it just might be useful. We also did some tests in the paper to see, okay, so what if we finally do find out what the spectroscopic redshift is? How does the performance change? And if we do slightly, the improvement in cosmology does go down, but I'd refer you to the paper for details. We use deterministic transition models. So for the upper limit performance that I will go through a little more, we use 2D Gaussian process regression for the full light curve. Of course, this is not realistic. But we also had a real-time implementation using an encoder-decoder LSTM, which yielded a slightly lower performance. I'm happy to discuss that as well. Then the new state, and then for determining the new state, we used 2D Gaussian process regression that was fit to the true light curve, which is a good approximation because you're essentially just sampling the next state. And we feed it back for the next day. And essentially, we came up with a deterministic off policy, fixed budget unit cost model that basically took the best action with the minimal cost for all Monte Carlo rollouts on a given day. We had this threshold of over no action that we were considering, because we did not want to start pursuing actions if they were leading to minimal improvement over no action situations. So there was this one hyperparameter that we optimize over. So essentially, what we have here is a bunch of light curves that were augmented. So this is the upper limit performance. It's not the realistic one, but even the realistic one has a similar situation, where what we find is that we were able to add photometry in places that were most constraining. And this is obviously tested against a random strategy. And we do some percentage points better than having a random policy. And what you essentially find is the system, if you look qualitatively as to what is happening, you will find that the augmentations were preferred around peaks, some around second peaks, because type 1a supernovae also have exhibit a secondary peak in some of the Reddit filters. So those were targeted as potential places where you wanted to optimize over. I'm sorry, I should have explained this plot better. So any given a given plot here just shows you what the ZTF public light curve was in faint, and the augmentations here were the ones that were strategized by the system, and essentially they were targeting phases that were most constraining for salt to a optimality, pseudo a. I can get into that as well. It's a trivial detail. And also the other thing that we noticed was that the allocations were made to be gap filling in nature. So it tried to cover, if for some reason the light curve had gaps, those were also regions that were targeted for filling up. And this is essentially just a plot showing the full results. So essentially, like I said, we were trying to minimize the uncertainty for various for SOL2 parameters, which were X0, X1, C, and photometric redshift, which of course is not used in cosmology, but still we try to minimize that. And what here is it's saying is what is the improvement for the uncertainty for each of these quantities over a random policy. And so we find that essentially, depending on the budget that you were considering, you could have anywhere between 2 to 6% improvement on the uncertainties. There was a higher improvement on the photometric redshift, but I'm not sure how useful that will be for cosmology. These numbers are small. I don't anticipate this would be groundbreaking for cosmology, but I think it was nice to see that you could do something smarter by allocating your budget, potentially having more impact if you targeted different wavelength regimes. And another thing we noticed was that there was 2 to 5% more improvement for these parameters for faint supernova 1E, for faint type 1A supernovae. So those were the ones with peak magnitudes greater than 18.5 mags. And the reason this was happening is because the algorithm was going after regions that were poorly sampled. So for the same reason, because light curves that are, by definition, not as informative, if you add more data, there you would actually see a better result. So it's indicative that potentially this could be useful for Rubin, but that remains to be seen. So I think I'm doing okay. Yeah, that's great. So I'm on my last slide. So with that being said, I think the main advantage of this procedure was that the algorithm is quite interpretable. If you look at the policy, it actually kind of makes sense. You can actually interpret why the algorithm was making the allocation decisions that it was, which is a huge thing to deliver trust in people who will potentially be considering whether they want to invest in using something like this. The other thing that was great was this algorithm is data acquisition failure intolerant, which means that if, for example, the particular strategy on a given day was not carried out due to weather or other conditions, the algorithm proceeds the next day as if nothing happened, and it just starts over. So it's good for that. It's not latency tolerant, which means that if you tell me that data will come 3 days later, make sure you account for that. The algorithm doesn't account for that. And as I mentioned, clearly the algorithm is not making optimal series of decisions. It's taking the greedy decision on a given day, and it averages over, but it still does better than purely random, which is good. And so possible extensions of this work, I think moving forward, would be to consider variable observing costs, depending on, for example, exposure time, or maybe different types of budget. So you may want to consider an allocation that's given to you over an observing season, and you want to allocate it for various events. And you can use other more complex choices of utility, depending on the science case. And I think there's a wide variety of science cases that would be benefiting from the situation. So I'm thinking spectra, I'm thinking of multi-wavelength and multi-messenger follow-up. That would be high value situations where something like this could be useful. And I think I just went over slightly, but I think I'm done. Hello?
We're here. Thank you for a really interesting talk. We have plenty of time for questions. Let's start the tour of the room over here.
Hello there. Really brilliant talk. I was hearing the terms budget and reward and allocation in this talk, and it immediately made me think of reinforcement learning. Would you call this work reinforcement learning, or is it a slightly different approach? And if so, how is it kind of different between the two? Because we heard in Emily's talk, we have active learning, and this seems to me like a reinforcement learning approach. Is that a right assumption?
So I actually wouldn't, I'm not sure of the semantics. I think some people would want to call it AI planning. So like since we are assuming that we know a model of the world, so this is not model free as you would see in Q learning. I would so this is probably like saying, okay, like I know the rules of the game. Let me just, solve for what the best strategy is. So I think it probably is more AI planning, if not, but I think broadly it touches on the broader sphere of reinforcement learning. Although I think reinforcement learning is much more detailed, and like I said, we've made several approximations that I would hesitate to call it reinforcement learning, but probably AI planning is a better bucket to be putting it in. Again, I'm not a semantics expert. Probably would ask somebody else about that, how to put it in a bucket. Yeah.
Great, thank you.
Great, thank you. We have a question here. There you go.
Thank you. Hi, thank you. I'm a big fan of this paper, actually.
Who is speaking? Sorry.
Sorry, I'm Federica. Nice to meet
Hi,
you.
Federica. Hi.
So the question that I have is on your last point, right? Because the work that you've showed is for supernova type 1a, for which we have very good theoretical models with a good empirical understanding of, variance around them, etc. And how optimistic are you about really enhancing the observations that we get for transients where the models are much more uncertain? And you mentioned multi-wavelength, so all the way as uncertain as the kilonova, which we basically don't know anything about.
I actually, so this is very interesting. So to be honest, the results of the work were a little disappointing for me, because I did walking in feel like this would just do so much better than just the nominal survey. And it was not as good. And, in hindsight, of course, ZTF was designed, one of the primary motivators was type 1a cosmology. So the cadence is determined in a way, is set in a way to be good for cosmology. So actually, I feel like, this setting, the problem choice was a poor one. Now that I look at it in hindsight, and it may be actually is true that if you look at some of these more poorly defined transients, as you call them, where the survey is not optimized for, it potentially could do better. Now, of course, you suffer because then the transitions, the models, etc. So the models that help you do the planning would be less informative and probably less certain. But with it, I feel, having tried this, I feel like that would be an avenue that we should definitely look at, because if you're in so either you're in a situation. So I think somewhere in the middle, the value of comfort would be Rubin for type 1a supernovae, which are great, but not the best sampled. And you may want to do multi-wavelength for 1as as a situation where you have good models. But there's also the other side where you may have poor models, so you can't do as your what do you say, your dynamics model is not as well determined, but you could gain larger impact. I think it remains to be seen, and I'm definitely interested in looking at that direction. It's high value for sure. And I'm happy to talk about it if any if you would want to look at that more closely as well.
Okay, next question. Can you introduce yourself, please?
She knows me. Hi, Ari. This is Bhagya.
Hi.
Nice to see you online. So I have two questions. So for one is, I think it's pretty straightforward answer for you, because how early or what number of detections do you need for like the Sol 2 parameters inferencing?
For for how many data points you need for Sol 2? So they do a chi-square minimization, and they fit for about so if it's a chi-square minimization, so I think you probably just need one, actually. If it's chi-square minimization for 4 parameters, would you want to need? Yeah, I actually don't know. That's a good question, but it shouldn't be that many. I mean, if it's a four parameter family of solutions, you for the best fit, if you're thinking about it that way, you need 4 data points, but you're not exactly doing sort of linear regression and model fitting, right? So
yeah, thank you. The reason why I ask is like, how early of a light curve can you be able to inference this? And like, I know peak in your work, the peak is a priority where you augment data, but I was just thinking, how early of a light curve can you be able to make that decision? We can talk more about it. Another question is a little more technical. Is there a reason why you chose the LSTM method? Because I see in your slide it's a little lower performance. Do you have any other like ongoing process where you would look forward for another model for doing the same work?
Yeah, so actually the second part feeds into the first part of your question, so I'm going to answer that. So essentially, as you know, when the situation, so when the episode starts, which is about 6 days, the state space is not only what you see, it's also the survey behavior. So we simulate Monte Carlo observations along the light curve. So when we feed it to, as for Sol 2 to query what the utility might be, you actually have more than the data points that you see for the first 6 days, because we've simulated some of them. We've also allocated some budget. So we do have a lot of data points on any given point that we're querying for Sol 2 benefit. And in order to get those estimates, we actually use 2D Gaussian process regression on the entire light curve. Now, this is cheating, because you're saying that when I see just a portion of the light curve and I'm going to estimate what I see, and I'm going to estimate based on the 2D Gaussian process regression, that's cheating, because you never actually see that. What you would want to do is forecasting, which is what refit does also, where you see the light curve and you estimate, you forecast what the outcome states might be. So the paper gives you the upper limit performance where you do this cheating portion. But then we do, so there's about a 3 percentage point drop in performance when you actually use forecast light curve. So we use forecast, and then you sample, sort of what you basically do the game where you're like, okay, should I do this? Should I do that? Which one am I doing better? So you do this based on 2 different ways, and one of them is more realistic, which is what could occur in practice, which is the second one. And for the encoder decoder LSTM, why the choice was made? Well, it worked well. I saw Ashley's paper. It worked. It looked good. I was like, okay, this will work for me. Although actually it wasn't really great. And I'm happy to share code for that.
Yeah, thank you so much. Yeah, FIA, Ari was a great mentor to me, so I know her very well. So okay, thank you.
Great. Our next question is from Gautam.
So Niharika, great talk. I am that annoying person who has to actually build pipelines from these things for Rubin. And Rubin, of course, we can't control the observing strategy, but we can trigger something like, say, the LCO network using a TOM toolkit to go study objects. Where is this source code so that we can start actually putting it in our pipeline? Is this available on GitHub anywhere?
Well, so even if so, so the published version will rely on 2D Gaussian process regression, which isn't implementable, like I said, because we are trying to estimate what various strategies would do in the presence of a model that is unrealistic. So that code you don't want because it won't work. For the encoder decoder LSTM, I'm happy to share that. So there was supposed to be a paper following up. I was just disappointed with the performance and decided not to publish. I don't know if that was a good decision. It was just not very great. So the results that you see here, we dropped a few percentage points. So it was like 1, and at best we went up to 3% improvement. So I was very sad about that, and I decided not to publish it. But if people are interested, I could potentially, I don't know, maybe put out a note or something that would then accompany with it the encoder decoder LSTM with it. I think I'm happy to talk about what would be most useful to do this actually. Yeah, not sure.
Yeah, I'll just quickly say, as a faculty member, the answer is always yes, publish, but more to the point, your results are given ZTF. And Rubin is not the same as ZTF. So it is not clear to me that your results will be the same in a different survey.
And not at all, it won't be. And if I had 10 arms like goddess Durga, I would probably do this for Rubin like in a heartbeat, but I can't. So when I get there, and hopefully, so I mean, I think there's also the caveat of if it just is just minorly helpful. I don't know, like if it doesn't do too well, what's the purpose of sharing it with the community? Maybe I guess for indexing, but I think the utility of the algorithm started becoming questionable in my mind when I couldn't get a realistically very good. This is already modest, it's not great. So I hesitated. So I feel like even if I do implement the Rubin side of stuff, it'll be a question of whether I actually get decent performance to happily share it with people. So I will keep this in mind, and if if we get there, which will be nice, and I will share it for sure.
I took the microphone just to encourage you to publish it. I think even if it didn't determine a really great improvement, I think it's really, you made excellent considerations about why that might be. And I think it would be very useful for, everybody to know that it's out there. Otherwise, somebody else might redo it and also not find a great improvement, and that would not be great.
Yeah. True. Yes, for sure. Thanks, Frederica. Giving me the encouragement. Okay, all right.
We have one more question here, and then we'll close. Can you introduce yourself, please?
Hi, my name is Alex Kim. I'm from LBL, Lawrence Berkeley Laboratory. And I guess the top level question I have is, I'm curious what the computational power requirements would be in the LSST era. But I guess a more, technical question is how many computes of your objective function are required to actually do the optimization?
Excellent questions. So how much compute power do you need for this to work in practice? Is that what you mean? So if I were to implement it, how much compute would I need for this to work? Is that one question? The first part?
Yeah, I got the microphone again. Yes, I mean, like scaling up in terms of the number of transients that Rubin will be discovering. And then just for simplicity, let's just stick to this supernova 1A problem.
So the rate limiting step actually in this, so for the real-time setting, even though we're able to estimate outcome states with an encoder decoder LSTM, because it's just a forward pass, that doesn't take long. The rate limiting step is SN Cosmo actually. It's not terribly fast, but you could probably and I have these numbers. So essentially, if you had a reasonably sized cluster, you could probably handle ZTF supernova 1A sample on a given window bucket. So like if you look at a 60-day window, and all Supernova 1A within it, with a few cores, you should be able to manage it in about 10 minutes or so. However, that being said, you could probably speed it up with an emulator if you put a Sol2 emulator in place, which we did not. So that would be another consideration. And another question about compute. So I, unfortunately, yes, I did burn a lot of compute power on this. So we used tensor processing units on Google Compute Engine. And yeah, I'm quite ashamed with how much carbon emissions we put out there. But I guess that's just what we're dealing with right now. So like in terms of like the compute power, I think regardless of how we move forward, if you're going to be using some of these deep learning techniques, we will be doing really not well for energy efficiency. I don't know if that was your second question.
I guess there's always the environmental concern, but I was also
Yeah.
wondering about just practically having the computing resources to be able to run these algorithms.
So yes, so for the hyperparameter optimization, so the encoder decoder LSTM, we had to search for a whole bunch of configurations for the architecture, and it was quite easily done on the Google Compute Engine. And so everybody pretty much has access to Colab and can trigger that. So that's not a problem. And they were quite fast and they're well optimized. So like, for example, a large grid of hyperparameter search, like a single training for a 2-layer encoder decoder LSTM took 5 seconds on the TPU. So I don't think the training will be an issue. I don't think this requires significantly heavy training. So I have a 3080 Ti which handled most of the real-time processing that's normal gaming grade GPU. I think anybody can have that. So and it's a public resource, the TPUs as well. So I don't think it needs specialized, nothing like Titan 5 or anything.
I'm so sorry to barge in. We need to wrap up this session.
Sorry.
Thank you again, Ari, and all of our speakers this morning for some great talks and great discussion just now.